Good morning, folks. So it's just a little bit of conditional probability today, just a little orange juice to get us going, as I've run out of biscuits and got nowhere to buy any more. So not to worry, on we go. Right then, conditional probability. So this is where some things do affect each other. I might know that the probability of it raining on a particular day in Ilfracombe is 40% at any time in the year. But if it rains today, as it probably will do, then the chances of it raining tomorrow will probably be a bit higher, because you've got the idea of there being rain in the air, and you get dry spells, don't you, and wet spells. So that's the sort of place that this comes from. So it's about probability getting more into real worldy type stuff. Although having said that, the questions won't necessarily be about that. So the first thing is that if you wanted to write about the probability that B happens, given A has already occurred, that would be written like that. So that is probability that B happens given A happens. So that's one, and then there's a few sort of knock-on things. This is all for independent events, so remembering that independent events are ones where they're not affecting each other. So rolling two dice, for example, would be a classic. So for that, you need to remember that the probability of A given B will always be the same as the probability of A given not B, because it makes no difference whether or not B happens. And that will always be the same thing, just as the probability of A happening itself. So B is making no difference whatsoever. And also, the other little rule for us to remember is that the probability of B given A is therefore going to be the same thing as the probability of B given not A, and of just the probability of B on its own. And within different questions, remembering that can allow you to make little equations that find out unknown things. Right, so first example, we've got 75 students, 25 of them study only humanities, 37 study only science, 11 study both. Now you might be asked to draw a two-way table or a Venn diagram for this. So have a little go at a Venn diagram first of all. Pause it, have a go. So your Venn diagram would have an overlap because there are some who do both, and that would be the first thing to put in. So you've got 11 there, you've got 37 studying only science, and you've got 25 studying only humanities. And then we've got 75 altogether. So if I add those up, I get 8, 13, 5, 6, 73. So there are 2 left over. So there must be 2 going in there. Right. That's the first thing. If you were asked to do a two-way table, that would look like, or what would that look like? Have a little think about it. Have a go, and then yeah, pause the video, all that. So you would have H and not H, humanities or not humanities, and you'd have science, sciences and not sciences. And we should also have totals running round the side. Now we know we've got 75 altogether. We know we've got 11 studying both. We know we've got 37 studying only science but not humanities, and we've got 25 studying humanities and not science, and we've got, well, if we add these up first of all when we were doing it, we would have got 37 6 there. What have I done? Wrong there, because that would get me, oh no, that's all right. 37 add 2 would get me 39, wouldn't it? And that does add up to 75. Just some trouble with my numbers there. 25 add 2 making 27. And you should always double check that all of these add up. So 48 plus 27 is 75. Check it on your calculator just to make sure. But there you go. So that's two different ways of looking at that information. And having done that, we've got some probabilities you may be asked for. So here's your 3 different questions you might have. Pause the video, have a little go, and then I'll talk through them. So the first one is probability, it's not S, it's not H, the intersection of both of them not happening. Now both of them not happening is actually these two here, possibly easy to see on the two-way table, not H and not S, it's those two there. So it's 2 out of everything that we've got is 75 students. Now the second one is what's the probability that someone studies science given they study humanities. So we know they study humanities, which means it's this line here out of 36 altogether, but we only want the ones that study science as well, so it's 11 out of 36. And we could have got that from here going, right, it's given that it's humanities, so it's those 36 altogether, and we just want those 11 there. And the last one is what's the probability that we study humanities given that we don't do the sciences. So not doing the sciences are these 25 and these 2. That makes 27, which is that number that we get down here, isn't it? Not doing sciences at all, because that's what we've been given. So that's our total number. And what we want is a probability that they do humanities, and that is nearly certain, isn't it? They're going to do 25. Right, our second example concerns dice and 4-sided dice. So what does a 4-sided dice looks like? Well, folks, it's a tetrahedron, which has a slight difficulty in how do you read it, because you get a point sticking up in the air. Now, sometimes you get the traditional way is to have the numbers written on the base. So there'll be the number 1 will be written 3 times, and if that's sort of see through over there, there'll also be a 1 going through there. And then there will be like a 2 there, and wherever a 2 would be right. So I'd have like a 2 and maybe a 4 or a 3 sort of signalled on there, but you just read the numbers around the bottom. Or the other way you can do it is if we've got another tetrahedron just there, you can get the numbers all written around the points. So you'll have 3 2s written around there, 3 3s written around there, 3 4s written around there, and it's whichever one is pointing straight upwards would be what you've rolled. Now, why am I going through that? Well, that's just a bit of fun, really. It doesn't matter. The question I've got for you is, if I roll 2 4-sided dice, so that's 2 4-sided dice, what is the probability that I get a total of 5 when I add the numbers together, given that I get at least 1 3? So I'm saying I roll my dice and I get at least 1 3. So I might get a 3 and a 2, for example. What's the probability of that? I'd like you to draw a sample space diagram for your 2 4-sided dice and all the different totals you could get, and see if you can come up with that. So pause it, have a go. So your sample space diagram should be labelled 1 to 4, 1 to 4, but we're adding, so that's giving us the smallest possible total of a 2. 1 add 2 is 3, 3 add 1 is 4, and so on. So our totals here, we're going to get 16 different possible things that can happen, and we get diagonal stripes of numbers going on. So 5 is the most likely roll, but we've already been given that we've got at least 1 3. So what that means is we're only concerned with what's happening here, and remember not to include that because those aren't events that are happening. So what we've got is 1 2 3 4 5 6 7 different ways that you can get at least 1 3, 6 of them being 1 3 and 1 of them being the double 3. And within that we've got the totals of 4 5 6 and 7. There are 2 ways of getting a 4, a 5 or a 7 and 1 of a 6. So it's a 2 in 7 chance of getting a total of 5 if you're told that you've got at least 1 3. And that's one question that you might get. The only other question that we might get on here would be, you might be asked a really annoying question of state one modelling assumption used in your calculations. So those annoying one-worders that they like to ask, but they're important because they're what this is about. And that one modelling assumption is that we're assuming that both these dice are fair, and that therefore the probabilities are all equal and independent. Okay, so it's just that the dice are fair. Now I'd like you just to practice on this, not a massive amount of practice, but we're looking at page 24, exercise 2b, and we're looking at questions 8, 9 and 10. But a lot of them use a slightly different way of logic of giving the information out to what we had in the last example. So I'm going to give you the beginning of question 8 right now, just to make sure we're heading in the right direction. Right. Here's your question. 120 students asked what they like, 56 what they like to watch, 56 watch sport, 77 watch drama. Of those that watch dramas, 18 also watch sports. Draw a two-way table. And you may notice these numbers add up to more than 120. So pause it and have a little go. So very similar to the one that we did before. You're going to want your totals things as well, so you want an extra column on the end. So there's our totals. We've got sport, not sport. We've got drama, not drama. Doesn't matter if you've done it the other way round. And the first bit to put in is the 18 who do both, because we know that can go in there. Now I also know that 56 are watching sport altogether, and 77 are watching drama altogether, and that then enables me to work out these ones here. So 56 take 18, well if I take 20 and 38, and 77 take 18, 57, 59, and now that I know that, I also know there's 120 altogether. So 56 plus 64 makes 120, and 59 plus 5 makes 64, so there are only 5 people who don't like either, and add those up to there gets you to 43. Now you should always double check that this line here adds up to 120, and it does, so that means I know I've got that right. And then there's some more questions on that, but that's just an important thing. And if you wanted to do it by Venn diagram, because you prefer Venn diagrams, you might want to do that first, then you can. You'd be putting your 18 in there, and then you'd have been taking your 18 away from 56, wouldn't you, to sorry, 18 away from 56 to give you drama, not liking sport, and so on, and filling it in that way. Okay. So long everyone, until next week when we get a bit more conditional probabilities and we start putting them into Venn diagrams, as we've already started to do a little bit.